So now that the instruction pointer is working, it keeps track of what memory location the CPU is supposed to execute. So what I need to do next is get this instruction pointer value transmitted to a register that can hold it stable for my RAM to access. That's what I'm going to be working on here. And also right now, this is only a 4-bit instruction pointer, but really it's supposed to be 16 bits. Once it's working with the memory address register, I'll update this to 16 bits. So I'll probably just add the memory address register right here. The register I'm using here is a 574 for the instruction pointer or the program counter to keep the data. So I'm going to use one more of these. Ultimately, it will be 2 because this is an 8-bit register. So I'll have 2 of them for 16 bits and then pull the data from the instruction pointer when fetch occurs. At least that's the idea. All right, here's another 574. Let's give it a shot. And we need to look at the schematic again, or the data sheet. So it goes sideways. The data coming in is going to be from the instruction pointer. So we're just going to get this perpetual data coming in, but we're only going to actually register it on the clock of the fetch. And then we'll output to LEDs. It should be a very short operation here. VCC and ground, and we can ground the OE as well. So let's do that first. So that's power, ground, and I'm going to ground the output enable because it's inverted. A 0 on the output enable keeps it outputting activated. And now we need to get the 4 inputs, 1, 2, 3, 4, from our instruction pointer because right now we only have 4. Then we need to output to more LEDs. So we need to add some LEDs here, 4 of them. I'm going to get 4 resistors and put them in. All right, I'm going to put some LEDs in. And now we need to take the output from the instruction pointer pretty much in tandem with them going to those LEDs over here. Man, what a mess this is though. Q1 should go into D1 of the other one. So 1 through 4 should go D through 4. So that's pretty easy. So I'm just going to put them in a row right here. So 1, 2, 3, 4. Orange is first. So 1, then yellow, then blue, and then the ooze. That's the output for the instruction pointer to send its data. Now we need the output into our LEDs. And I'm trying to line up the bits to be least significant bit on the right. So that's why the leftmost is going to the rightmost. And now all we need to do is pretty much connect the clock, I think, which is at top right. Right there is a clock. So that needs to come from the CPU state machine, the fetch instruction, right to the left of this purple wire. So I'm going to plug him in there. So when fetch is hot, we will hopefully synchronize. Turn on power. Hopefully nothing explodes. I think it's working. This worked very well the first time. We can see now that the memory address register is 1 behind the instruction pointer always, which is exactly what we want. We want it so that when a cycle starts, the instruction pointer is at 0. So the memory address register grabs that 0, then he goes up in the decode. But by the time decode is happening, the memory address register would have already had the correct address and done its job. And then when the next cycle comes now, instruction pointer has already incremented on the previous cycle, so memory address can get 1, and then it repeats. So instruction pointer is 1 ahead after handing it off to the memory address controller. So ideally what this guy would be doing right now is during the decode step, tell the memory controller, the RAM, to output the data from this address. And then during the execute, the last phase, we would actually run that command. So next up is pretty much to add the RAM. I had already tested the RAM chip with the Arduino because I wasn't sure how it worked and I wanted to do all my testing with code and not have to wire things up and then unwire it when there's a problem. So I have an understanding of how it works. And now I think I'm ready to add it to a breadboard and wire it up so that we can fetch the actual instructions at the address in the memory address controller. And then we can move on to executing it later on when we have our instruction decoder. So I'm also partially thinking right now about just redoing it now and expanding it to its 16-bit variant. So surprisingly, this worked on the first try, and I had to take a quick break. So I've actually been leaving it running like this for hours just to see how long it takes to get to 64,000, because we actually had the full 16 bits here that we're going to be using for this project. So the wiring, I think, could be a lot better, but at least I kept most of the messy parts together. And then the display port has a nice sort of Rainbow Road cable here, just connects to the different nibbles, we'll say, the 4 bytes, 4 of them. Unfortunately, I undid what we had before with the instruction memory address register. I'm going to call it the IMAR. We had the IMAR earlier set up, but now that it's 16-bit, we just have to do it again. So I guess what I'll do is I'll add another one to make it 16-bit and get it working again. I'll put the display port next to it, so we'll have its own display port built in. All right, here's another 574, so I'm going to put him next to the existing one. I would plug out the power, but he's just a little bit too pretty for me to turn off already. I really like how he looks. And surprisingly, it was a one-shot, so I didn't have to change anything. I connected everything and then turned it on and it was working, so I'm pretty proud of that. It shows that the practice from the prototype really helped. So I'm going to shift everything down here, I think. Ground is in on this guy, so we have ground, we have VCC, and then we have the output enable grounded with the next door neighbor's ground guy. So he's grounded too, so that means this is grounded. And we have power, and this output enable is grounded. So output time. Okay, so at the risk of confusing myself later, on the last one, on the instruction pointer, this is my bit 1, and then my most significant bit is all the way over here. What I'm going to do here is flip it so that I can use the same wires and end up going the same distance away on my display port. I think that probably makes more sense to do it this way. So let's see how that goes. So there's 1, 6. Okay, so this should be it for the first one. So that's 8. That's relatively clean, I think. I think it's the nicest wiring that I've done for that amount of wires in one place. 16 wires here. And we need to put in resistors. All right, so here's our 16 resistors. Hopefully all the cables are going in properly. And now what we can do is just add our LEDs, and we should have our 16-bit display port. And then we can get our inputs into here from our instruction pointer. All right, here they are. So now what we need to do is get our outputs again. This is going to be my least significant bit to reflect here. The least significant bit on the output is here. So I guess I'll just connect these in, and then I'll need to connect the clock. So let's try that. 3, 4, 5, and 8. All right. I think this is connected properly. I do need to connect my clock. These two clocks are connected, so I need to connect the actual clock to the decode signal. Sorry, the fetch signal, right? So the fetch, put that clock in here, and fetch is all the way over here off the map. My wires are actually not long enough, so I guess what I'll do is I'll make a little fetch location right here. All right, so fetch goes here. Just make it pretty close right here. Blue cable into, I'm gonna put it around, make it a little into decode. Okay, I think we should plug it in and see what happens. I don't think it's gonna work. Oh, I know why I don't think it's gonna work. It doesn't have power. I don't need power here, but I do need ground. So I need to share the ground. Ground goes into ground. Well, let's plug them in and see what happens. So far it looks great. However, we have a light over here that's always on, but if I don't pay attention to that, it's working very well. We are again one instruction behind, or one address behind the instruction pointer, which is perfect because he's fetching it from the instruction pointer right before the instruction pointer increments for the next instruction, which we may modify how that is. We're going to have to modify it, I think, as we get deeper into the system. But I need to figure out why this guy is on. I'm assuming that this VCC, maybe I plugged something into VCC by accident. And see where he's plugged in. He's really not in VCC. I thought he would have been a VCC. So I don't know what's causing that light. I'm not really too worried about it right now. I think this is really good progress, and it's a bit late for me, so I'm going to pause here, and I guess I'll try and figure out what is causing that light to stay on tomorrow. But fortunately, it's the one bit we don't need, so that's a bit of a lucky strike for us. So what I'm going to do is turn up the speed real quick, just make sure everything looks good. So if I turn it up all the way, we can see that everything does look pretty good. Although I think there's a dead light. This light seems to be dead. Oh wait, it's not dead. There's no resistor going into it. 2 resistors are going into one place. There we go. But yeah, so here's him at the maximum speed that we can do, and I think it looks beautiful. So we have our instruction pointer here incrementing, and we have our instruction memory address register, the IMAR, who is going to be responsible for pulling the code the instruction from the RAM. So next up, we need to get the RAM working so that we can draw this address from the RAM. And then we'll end up having to put an instruction register where we put that instruction and we can get to decoding. And since I'm obviously much more comfortable programming, I did do a little project to integrate with the RAM with an Arduino. I don't know if you saw it, but I basically just tested the pins and everything and the sequence with code so that I don't need to fiddle with it too much with hardware. I know exactly how it works, so I don't need to try and learn it as I go. That might become very useful later on when we're trying to write programs and stuff. We can actually use the Arduino to program the RAM, but I'm doing everything hopefully with hardware. So I'm going to make a memory controller next that can write data to the RAM or read data out of the RAM. I think that will be a really good step. And then after that, we can integrate the IMAR into that RAM. And every time we get a fetch, we can actually grab the data, the byte that's at that address in the RAM. So that will be the goal. So that's a pretty big step right there. And what I've been thinking of doing, since I'm at the end of the video, I feel like I can take my time more and not be at risk of wasting people's time too much. I need to draw out my idea of what the CPU will look like. I'm not using a book or anything or following any other examples. I'm just trying to do it in a logical way. And really what I'm going for is simplicity and atomicity, if that's a word. I want it to be as discrete and as atomic as possible. So I'm really trying to avoid things like microcode and trying to limit how many state machines. We obviously have one state machine already on the CPU, but that one is a bit hard to avoid. I don't really know an alternative to that. And I'm pretty comfortable with the fetch, decode, execute cycle, at least in theory. So I guess what I should do is write out or draw out in one of these videos what I'm planning. I do have a bit of a plan. I've been thinking about it for a few weeks on and off, but a lot of it is definitely just trial and error and just knowing the main parts of the CPU that we need to build and trying to make them connect together. So this has been really great. Really happy how this turned out. Both of these were pretty much one shot. Now this one is technically a fail because that last bit is turned on. But again, very fortunately, we don't need that bit since our RAM can't even use it. But yeah, one-shotting the 16-bit version of the instruction pointer was great, and almost one-shotting the memory, the IMAR is fantastic. So thanks very much for joining me. And thanks again to Flex, Aiden, and Techno for your suggestions. I really appreciate it. The output enable that you guys suggested to tie down was very fortuitous because, I mean, that fixed the problem as soon as I saw it. So that was great. And Techno, I will definitely try and get that button working because it will be really helpful in the future. So thanks for hanging out, and I'll see you soon. So here's our instruction pointer plugging away, and there's one little issue. As I turned up the clock, we can see how fast the clock is going now. The counter stopped counting upwards. It's ending at the value of 3 or 2, and then it's going back to 1. But I got some really helpful comments that solve this issue. Flexair said I would connect OE to ground the output enable to make sure it doesn't float, and Aiden said the 74HCs in general just don't like floating points. So when I do put this to ground, then we can suddenly see the counter start going upwards all the way. So really helpful comment. Thanks very much, Flex and Aiden. And there was another really nice comment from Techno. He was telling me how to debounce this button that seems to need a bit more debouncing, but I don't have the capacitors that he mentioned. I think I have some at the office. I have a kit there, so I'll try and get that tomorrow.